Hello everybody, I congratulate you with the new academic year, right? And you see new rules. Last year it was allowed for lectors to speak without any preserving tools from COVID. And now you see new rules. We should use something, so I prefer to use that one instead of this, right? Because to speak with this, it's even worse. Okay, so officially this course is called sequences and series of functions and functions of several variables, right? Very long title. And you see, I hope you remember that sequences and series of functions were given during last semester, right? And power series were not included into the exam program, hence power series will be included into the program of winter exam. And also I hope that your seminar teacher gave you or will give next future the first assignment. The first assignment I prepared, but other two not yet, unfortunately. I plan to do it in next week or even next decade, maybe it's better to say. So I'll start, hence I can start with functions of several variables, right? And how it is planned, I'll give you also parts about different spaces which you can find in your textbook in places of the first year. So sometimes there were definitions about some spaces, linear, normed, Euclidean spaces, and so on. And now we start with all of those definitions together. So we start new chapter. Let it be chapter 1 because this is new year, right? And chapter 1 is called vector functions and topology of the space Rm. And section 1 is about the space Rm. This space is, I guess you are familiar with this space from linear algebra, and so I'll use both algebraic properties of Rn, but also we'll need to consider limits and so on. Hence we need topology of Rn, and I'll start with recalling definition. Maybe I'll do it for general. Okay, first of all, what is Rn, right? Rn is the set of all x's, x, x1, so on, xn, where xi are in R for all terms. So these are ordered n numbers and real numbers, and we consider the set of such vectors, right? So what is about algebraic structure of Rn? A linear space in a more general setting, right? A linear space, let's say E, is a set of vectors such that for any x1, x2, let it be vectors in E, there exists a sum again in E, and for any alpha in R and for any x in E, there exists alpha times x again in E u vector, which satisfy the following properties. So I'll collect all of those properties now. First, okay, I'll indicate by capital Roman digits what is related to each of operations. So we have two operations, right? Addition in vectors and multiplication by scalars, by numbers. And so one indicates it is related to the sum, and we have several properties which are related to the sum only, right? What they are. So commutativity, commutative law, so for arbitrary x1, okay, let it be xy, it's better to write like that, x plus y equals to y plus x. 1b, associative. Law. So for arbitrary 3 vectors in our vector space, we have x plus y plus z equals to x plus y plus z. Also, we have neutral element. So there exists 0 vector in E such that for arbitrary x in E, we have 0 plus x equals to x. Of course, you can change because of the first property, right? And the last in this group of properties is opposite vector. So for arbitrary x in E, there exists element minus x such that x plus minus x equals to neutral 0 vector. So these are properties which concern only addition, right? Only addition. Now, what is about properties for multiplication? So, okay, 2a. For arbitrary numbers alpha, beta, and for arbitrary x, we have alpha times beta x equals to alpha beta x. That is a property which is related to the product to a number, right? And 2b for arbitrary x in E, 1 times x equals to x. That is also a property which is related to the product only. And now properties which are related, sorry. Firstly to C, again for arbitrary alpha, beta in R. For arbitrary x in E, we have alpha plus beta x equals to alpha x plus beta x. And then a property which contains both operations. So for arbitrary alpha in R and for arbitrary 2 vectors in E, we have alpha times x plus y equals to alpha x plus alpha y. Yeah. Now that is a complete list of properties of a linear space, right? And I guess you studied it in linear algebra, so I don't want to spend too much of time in considering general theory of linear spaces. Maybe just to recall you how it works. A short example of an assertion and how it can be proved. So, a proposition. Proposition 1 for arbitrary x in E, minus 1 x equals to minus x. Yeah.
Why is there no commutative law for multiplication?
What do you mean by commutative law for multiplication? You cannot change alpha and x. There is only multiplication of a vector by a scalar, right? They have different nature, vectors and numbers. Okay, so how to prove it? First of all, I'll start with proof. First step, we'll prove that minus x is defined uniquely. You see, it was not said that opposite vector is a unique vector, right? So, by contradiction, suppose there are two. Both are opposite, right? Two versions of the opposite vector. There are two possibilities. Okay, then write down firstly x plus minus x, let's say 1, plus minus x 2. Because of the second, better to say 1b, right? Associative law for the sum, doesn't matter where to put brackets, right? So I may forget about brackets, but if you want, we may put brackets like that. And then what is it? Because of the property of the opposite vector, that is 0 plus minus x 2 or minus x second version, right? From the other side, what can we do? We can change the order, right? Change the order here and write it like that. Minus x1 plus x plus minus x version 2. Then what we obtain after that? Here, because of the property of the opposite vector, we have 0. So we have minus x first version plus 0, and that is minus x first version. So you see, minus x second version equals to minus x first version, right? It means there is only one version of the opposite vector. Okay, that is first step. Second step. 0 times x is 0. 0 vector, right? You see, there is no such a property. So how we'll prove it? Okay, for arbitrary, what are properties of the neutral element? This element is such that when we add it to arbitrary, we obtain the same element, right? So let us write for arbitrary x in E 0 x plus x. So what is it? According to the property 2b, I can replace this x by 1 times x, right? After that, I can use property 2c, right? 0, 1. So I can rewrite it as 0 plus 1 x. After that, properties of real numbers 1x, and once again to b, we obtain x. So 0 times x has the same property as neutral element, hence it is equal to 0. Once again, we need to prove uniqueness of 0 element. I'll not prove it now, it's too much of algebra, but you should do it, right? So here I refer to uniqueness of the neutral element. So from this property, because this is valid for arbitrary x, we obtain this is 0 element. Okay, last step. Now we are ready to prove the claim, right? So I'll check that for arbitrary x in E, we have x plus minus 1x equals to 0. If this is true, then because of the first step, right, we obtain what we want to prove, that minus x is indeed equals to minus 1 times x. Because opposite element is unique, and this is such a property is the property of an opposite element, right? So that is, we need to check, right? We need to check this property. Okay, how to do it? Let us write in details. So property 2b says that x can be written as 1 times x. After that, we can refer to 2c. So 1 plus minus 1x. After that, we have 0 times x. And lastly, second step says this is 0, right? So finally, we refer to the first step, and the assertion is proved. So you see, nothing difficult, but nevertheless, something should be done, right? If you want to do it sufficiently rigorously. Of course, I don't plan to go deeply inside linear spaces. I hope you did it in linear algebra. And 2 words about real spaces, right? Better to say, what was before was about real spaces, and if we replace instead of R put C, then what we obtain, everything else is the same, and what we obtain, E is a complex linear space. In general, the difference between real linear spaces and complex linear spaces is so-called complex structure. So definition: complex structure on a real linear space E is a linear map J from E to E such that J squared is minus identity on E. So what is simplest example? The simplest example is C, right? The set of complex numbers. We can identify it with R2, right? And how we introduce complex structure on R2. That is the space which sends arbitrary pair of real numbers x, y into this pair minus y, x. What it means, this complex structure? Look, if we consider this pair of real numbers as a complex number, right? Then how to transform this complex number into that one? What you should do? Multiply by I, right? I times this, right? So what is complex structure on R2? Is this linear map? This is linear map, right? And it is multiplication by I. And that is in a way how to introduce complex structure with this J, right? And for example, okay, for example, we can introduce, that is a lemma, in fact, right? And maybe I should firstly, of course, I should mention lemma 1. Rn is a real linear space. Cn is a complex linear space. And I guess I don't need to spend the time to prove it, right? Because what is sum of two vectors is obviously, right, component-wise, and product also obvious thing, component-wise multiplication by scalars, right? And lemma 2, R2n has a complex structure given by multiplication by matrix J, which is 0, minus 1, 1, 0. So block matrix, everything is 0, right? Others are zeros. And you see, one block corresponds to that linear map, right? 0, minus 1, 1, 0 corresponds to this transform, right? If you multiply vector xy by 0, minus 1, 1, 0, you obtain minus yx. So that is a generalization. So if you introduce such a complex structure, then you can identify R2n with Cn. That is a way to consider complex linear spaces Cn. Also, for example, you can consider the set x1, x2 in R2 such that x2 equals to 0. So what is it? You fix second component of vector to be equal to 0, right? You have a real line, right? Yeah, so it is isomorphic to R1. I don't want to introduce formal definition of isomorphism. You consider it in algebra, I guess, right? So obviously that is true. So that is real line. Analogously, Z1, Z2 in C2 such that Z2 equals to 0 is isomorphic to C1, right? And it is called complex line then. That is a little bit strange. You remember we considered complex numbers, right? And complex numbers are on complex plane, right? But now this complex plane C1 is called complex line. When you work with several complex variables, that is unfortunately standard term, complex line. But remember, this complex line is two-dimensional object. Okay? Both Z1 and Z2 are complex numbers. C2, right? Yeah. Both are complex numbers, right? Yeah. So that is you see, terminology. So sometimes plane is called complex line. That is when you need to consider several complex variables, that is rather convenient. Okay, we will not go into these details. Now, more algebraic structures. More algebraic structures. I have 5 minutes. Next definition. A real linear space E is called an Euclidean. Euclidean like that, right? Euclidean space if there exists a map from E squared to R such that, so first, for arbitrary x in E, x times x is non-negative, and x is 0 if and only if x is 0 vector. That is first property. Second property or axiom of an Euclidean space. So for arbitrary x, y in E, x, y equals to y, x. Symmetry, right? And the last linearity. So for arbitrary alpha, beta in R, and for arbitrary x, y in E, we have alpha x, y, z in E, alpha x plus beta y times z equals to alpha x z plus beta y z. That is about Euclidean space. So these brackets, we call it scalar product, a map. Definition. There is a question, what is definition of a map? No definition yet. Something which has these properties, nothing else. Right? So for arbitrary pair of vectors, we put into correspondence a real number. And this correspondence should satisfy those properties. Nothing else yet, right? And after that, we can prove a next assertion, lemma 3. Rn is an Euclidean space with scalar product given by standard way xi times yi, right? That is standard definition of a scalar product in Rn. I guess you don't need to prove here, right? Everything is obvious. Because scalar product onto itself is sum of squares, right? Which is non-negative. And the sum of squares is 0 if and only if each of coordinate is 0. So the most untrivial is the first one. Others are absolutely obvious. Theorem 1. Cauchy, Bunyakovsky, Schwarz inequality. So the book which I was talking about was published quite recently, and it is called, I think, Cauchy-Schwarz inequality and around. So there are many different combinations. In Russian Wikipedia it is called Cauchy-Bunyakovsky. Also in many books it is called Schwarz inequality, so many different combinations. Okay. And I'll give it in general setting of a Euclidean space. So let E be an Euclidean space. Then for arbitrary x, y in E, we have modulo x, y less or equal x, x times y. Where to put square? Let it be both. Square root times square root. With and the equality sign holds if and only if x equals to lambda y for lambda in R. For a real number, you have proportionality of vectors or collinearity. Equality. Proof. Consider such a construction. So x plus lambda y times x plus lambda y. For arbitrary real number lambda. Then what happens? Look, we have a vector, right, in our space E, and we multiply by itself, hence it is non-negative, right? So this construction is a non-negative number for arbitrary lambda in R. So we have something which is always non-negative for arbitrary lambda. Okay, x, y are fixed, arbitrary, but we fix them. Now let's consider what is it. Look, x plus lambda y times x plus lambda y equals 2. So we'll use properties of the scalar product. So what is it? Okay, using third property, right? What we know, we can write x times x plus lambda y plus lambda y times x plus lambda y. That is third property of the Euclidean space. Then, using second property, we change the order. So x plus lambda y times x plus lambda times x plus lambda y times y. And after that, once again, we use third property. So x plus lambda y x plus lambda x y plus lambda squared y. Once again, using second property, we can observe that second and third terms are equal, and we can rewrite it as follows. So I'll start with lambda squared y plus 2 lambda x y plus x. And recall what we know. We know this guy is non-negative for all lambda in R. But what is it? That is quadratic polynomial, right, in lambda. Quadratic polynomial in lambda. Okay. Of course, quadratic if y is not 0, right? But if y is 0, then what happens? Here we have 0. If y is 0, then what we obtain? We have a linear polynomial, right? And linear polynomial is always non-negative. How it can happen? It can happen only if the coefficient is 0, right? So if y is 0, then this is 0 as well. Otherwise, it's impossible, always non-negative. Hence, what we obtain? If y is 0, here both left and right hand side of our inequality are zeros. So I can consider only non-zero y's, and in this case, this is indeed quadratic polynomial, right? Okay, quadratic polynomial is always non-zero. It happens if it has discriminant with discriminant non-positive, right? If it is positive, then there are at least two different roots, and between them we have negative, right? Hence, discriminant should be non-positive. So what is discriminant? I will write discriminant over 4. What is it? xy squared minus xx times y. So it should be non-positive, right? And what is it? That is precisely what we want to prove, right? And also, what is about equality sign? So look at this proof. So equality sign, what it means? Discriminant is what? Discriminant is 0, right? Discriminant is 0 means our quadratic polynomial equals to 0 at a point, right? And when it is 0, this is 0 if and only if x plus lambda y is 0. That is practically up to sign here, right? So lambda here is minus lambda from there. That is a little bit not very convenient, but you see the theorem is proved completely, right? So very simple proof. And what is the consequence for our space Rn? So I forget. Yeah, corollary. That is corollary. So corollary for arbitrary x, y in Rn, what we can write? So modulo of product, modulo of the sum xi, yi less or equal square root of sum times square root of Of course, you can ask me why I inserted modulus, because xi squared and modulo xi squared is the same, right? But I did it because of the next generalization for complex linear spaces, right? So what to do? Okay, concerning this inequality, I guess no questions, right? Because we just substitute the definition and that's all. That is x times x, y times I. Modulus I inserted here, definitely I could do it because x squared and modulo x squared, they're equal for x real, right? Yeah. So, then more generalizations. And maybe I should also, yeah, first generalization is the following. That is definition. If E is a space, is a linear space, with again such a product such that two, three are satisfied, but instead of 1 so the following holds for the following property holds. If for arbitrary y in E we have x times y equals to 0, then x equals to 0. Okay. Then E is called pseudo-Euclidean. Space. Pseudo-Euclidean space. And the most important example so-called Minkowski space. So what is it? R4, and the product is defined as follows. So we use the following numbering. The following numbering, right? 4 coordinates and x0, y0, minus x1, y1, x2, y2, x3, 3, y3. So Minkowski space is very important in relativity theory. 0 coordinate is time, other coordinates are space coordinates. And this scalar product definitely it doesn't satisfy the first property of the Euclidean, right? But nevertheless, it satisfies that one, and that is a very important example of pseudo Euclidean space. We will not consider it in more details. And now, what is about complex Euclidean space? Complex Euclidean spaces, okay, let me give a definition. A complex linear space E is called a complex Euclidean or what is more often used, unitary space if there exists a map E2 to C now, such that okay, first and third property are the same as for real, but the second is different. For arbitrary x, y in E, we have x, y equals to y, x conjugate, complex conjugate. So the only difference is here. And also Hermitian spaces, they are called. Hermitian also. Unitary or Hermitian. Okay, it doesn't matter. So, and once again, first example, and it will be lemma 4. Cn is a unitary space, right? But now the product of two complex vectors z and let's say w is given as follows. This is the sum zi times wi conjugate. Okay, I is not a good idea to use for complex numbers, right? Let index be j. So you see, conjugate should be here. In this case, if you multiply a vector by itself, right, what happens if you put zj and wj equals to zj? You have zj times zj bar. And that is modulus zj squared. That is why I used modulus in the corollary, right? Yeah. So this corollary will be valid for Cn as well. But corollary of what? Theorem was given only, theorem 1 was given only for real Euclidean spaces, right? And it was proved. But it turns out that the same result is valid for arbitrary unitary space. And, okay, let me prove it. So, theorem 2 is Cauchy Bunyakovsky. Okay, how I wrote Bunyakovsky like that. Unitary spaces. In fact, it looks like that inequality, so nothing changed except for the proof. Let E be a unitary space. Then for all, okay, let it be again ZW. In E, we have modulo ZW less or equal square root of ZZ times square root of WW. With equality, now equality sign similar, but for a complex. For a complex with equality sign. How it was called? Holds. Not with and the equality sign holds if and only if there exists lambda now a complex number such that z equals to lambda times w. So proof so we take arbitrary z and w in our unitary space and put zw equals to modulo times e to the power I phi. So exponential form of a complex number. We know that complex product, scalar product is a complex number. Scalar product is a complex number, and we represent it in the exponential form. And after that, we consider similar thing, but with, so consider now z plus lambda times e power I phi w times the same. So once again we consider scalar product of something by itself. Lambda is real here. Lambda is real. So this is non-negative once again for arbitrary lambda real now. That's important. Okay, and now let us calculate what is it, this scalar product, by properties of scalar product. So using property 3, we can write z times z plus lambda e power I phi w plus lambda e power I phi w times z plus lambda e I phi w. Now I understand. I made a mistake when I said 3 is same as for real. Not true. For complex, I should take complex here. So 3 should be replaced by, for arbitrary alpha beta in C. That was mistake. Yeah. And for arbitrary x, y, z in E, we have alpha x plus beta y times z equals to alpha xz plus beta y z. So third property is completely the same except for letter C here. That is the only thing which should be replaced. I forget, I'm sorry. But that is very important, of course. Because here I use it with a complex number, right? That property with a complex number. Okay. After that, so here I used third property, right? Now second property of the unitary, we change the order, right? And when we change the order, we have to put conjugate. So we obtain z plus lambda e power I phi w times z, but conjugate, plus lambda e power I phi times z plus lambda e I phi w times w conjugate. Okay. Now, no. Let me erase Koszybunikovsky for Euclidean. Okay. So once again I use third property. So I'll go with using of the third property. So we have zz plus lambda e power I phi w z conjugate plus lambda ei phi z w plus lambda ei phi w conjugate, and then we'll use property of complex conjugation. We know that complex conjugation of a sum equals to sum of conjugates, right? Conjugate to the product is equal to the product of conjugates, right? And also remember that z times z and w times w are real numbers, right? So conjugate to them themselves, right? So what we obtain? Z, after that, lambda is real, plus lambda e power minus I phi conjugate to e I phi, right? Conjugate wz is zw by second property, right? So also second property is used here as well, right? Then plus lambda e I phi zw conjugate, right? and plus lambda squared e I phi as a common multiplier, right? So e I phi times e minus I phi is 0, w. And lastly, remember the definition of e power I phi. Look, zw times e power minus I phi, that is precisely modulus, right? So that is a real number. And what is written here, I can put like that, conjugate minus here, right? That is also a real number. Conjugate to a real number, it's itself, right? So I can write like that, z plus 2 lambda modulus zw plus lambda squared w. And now you see what we have here. Real. Lambda is real. Now everything is real. Real quadratic polynomial, which is non-negative for arbitrary real lambda. Hence, discriminant is non-positive. What is discriminant here? Modulo of zw minus zz times ww. That is non-positive, and it gives immediately the inequality which we wanted, right? Next, squared, yeah, squared here, right? Squared. Next, when we have equality sign, if we have equality, it means we have equality here, right? At a point. If we have equality for some value of lambda, what it means? It means that z equals to this guy with minus. And that is precisely what was written here, but now this new lambda is minus lambda e power minus I phi, right? Minus lambda e power I phi here. This guy with minus is that lambda, complex. So theorem is proved, and now corollary. Okay. No time to rewrite it, hence, sorry, corollary. That one. And now modulus are used. Yeah. This corollary now works for Cn, and now it's important to put here modulus, right? Because if they are complex numbers, we should put modulus here. Okay, and it seems that's all for today. Yeah, because, and practically we finished everything with algebraic properties of Rn or of Cn. So I guess I repeated algebra. Most probably you studied it. Yeah? I don't know. Did you study it in algebra? Everything. Nothing new. Cauchy-Bunyakovsky-Schwarz also? No. Yeah, that is algebraic, you saw, right? But nevertheless, usually it is given for analysis, although it is algebraic thing. Okay, that's all for today. Thank you for your attention.